with that, I'd like to introduce Gharib, who is a professor at Caltech, has studied, vortex systems and fluid dynamics, but I believe is going to focus today on a lot of the discussions and probably follow up on some of the things that even Stephen said yesterday on autonomous systems for a variety of scientific applications. Thank you.
Good afternoon, and I'm really excited to be here and enjoying all the talks that the rest of the day. As Rick mentioned, I'm Gharib, I'm a professor at Caltech. By training, I'm a rocket scientist, but I do everything else but rocket science. In this lecture talk, I would like to kind of change the flavor a little bit and look at the autonomous systems from the point of view of machine learning and AI. In 2018, we started a center at Caltech called Center for Autonomous Systems and Technologies, basically bringing all the groups and departments that work on different aspects of autonomy, also JPL, and in order for students to see the whole spectrum of what we're doing rather than just in the departments. The concept of bringing machines and humans together is not a new concept. Carl Sagan is saying that the world where autonomous intelligent machines work alongside of humans and augment human abilities. And that's a very important goal and novel goal, in my opinion. And of course, JPL and Caltech, they are not new to this field of autonomous systems or how to actually use them. If you look at all the missions that we have run with JPL, it works. So we start from Viking, that was first basically robotic landing on Mars, to Pathfinder, the first rover on Mars. We basically developed an automatic kind of approach. That means there is the orders or lines of the duties that they should do, and they just follow them. And if we lose the operator or something goes wrong, they're in trouble. And the improvement, the evolution towards autonomy was the start of the Spirit and Opportunity, where they were semi-autonomous, and then the third side also Ingenuity, that they had a good host of autonomous, the functional aspects. So the result was that we had a fantastic operation. Practically, we landed a crane on Mars, and during 7 minutes of they call it 7 minutes of terror, this machine was totally autonomous, and we were able to solve some of the problems if they had the result. And then consequently, it was Ingenuity, which was a Mars helicopter, that actually the time for the signal go from Earth to Mars was 17 minutes, much longer than the mission that it had. So it had to do everything autonomously. And actually, during the process, solve some of the problems that we were quite amazed at how could you do it. So with that background, the center that is a combination of Caltech and JPL also started to challenge itself that, what can we do in order to bring autonomy into or autonomous system to a new age of the machine learning and AI. So one obvious shortcoming in this kind of designs, all these gadgets that we see here, is that they are built, and after they were built, they were told that not to be smart. That means you just put the brain. So there are two different vertical axes. So we wanted to see if we can use AI and machine learning in the process of design, like a human being, from the embryonic stages to the time you die. We basically are functional, but the machine's changing the emissions, from your heart to your liver. So at every point we are a functioning machine, and we are going through the basically development and the functionality that we are today. So the idea was that to be able to use AI and machine learning for designing the system from the beginning, from the time that they actually started thinking about what components should go and how we should approach the whole process of design. Now, to do that, we decided to set up some, I would say, ambitious goals. We call it moonshots, and also to make sure these moonshots are not really the missions that only Caltech or JPL is trying to solve, but try to actually inspire the community in order to overcome the challenges that we have in the area of the autonomy and autonomous systems. So these are the five basic moonshots that we designed for our objectives. First one is Explorer. Let me explain what they are. Imagine that a group of agents, it can be rovers, bipedals, drones, and they do a mission together. In the process of that, they start to learn how to solve the problems for each other. That means, in this case, from Professor Aaron Ames's group, the dog actually sniffs the targets and communicates with the other two agents, and basically decides that, say, the most expensive one, which is the Segway, should follow. So this one really totally depends on the information it gets from the others. Ideally, the mission was to have some of these robots go from Griffith Park to Mount Wilson in Los Angeles, and in the process, they just work together. And perhaps the same hardware that started would not have been the same hardware that arrived at Mount Wilson. It's going to be different machines because they're going to be replacing each other. But the DNA of memory that they collect and how they approach the problem, to solve the problems, was important for us to understand that how they work together. So, and definitely the outcome would have been, or will be, going to help our mission to Mars when we do sample collections, and these sample collections are not really directed by the operator of the JPL, but actually the machine itself decides, this is interesting, help me to go and get the sample and return. The next one is Guardians. These are basically the dormant sensors that we can strategically put them around, areas, especially in California fire, the flood, or earthquake, and they are dormant, but they are sensing. And once they sense, they wake up. And for example, in case of fire, they do smell and also look at the wind direction and do the triangulation and identify within, the 50 feet where the source of the high temperature is. And then the idea is that to be able to have robots that can go and either inspect what's happening or even interfere and try to solve the problem, or prepare the environment for the first responders as they arrive. For example, set up the Wi-Fi. This is a project that is sponsored by DARPA and JPL did for projects like what I just described, to be able to actually, the robot decides where the fire is, and goes and tries to extinguish. The next, of course, these are just samples. There are many other projects like the Guardians. We built a box and we put it in an island in Turkey, Georgias. It's a small island that every time a hurricane comes, this island disappears. And then within 6 months, life comes back. So our biogeologists are interested to know how nature repairs itself. Every time a hurricane passes by, they send a graduate student over there with a drone. And most of them, they think they're going to resort, but actually this is a deserted island that they have to go through a harsh situation. So what we have now, this box is sitting there, and every time we need it, opens up, the drone comes up, takes the information, uses multispectral cameras, and then sends it back to the geology department of Caltech. So you can see that this machine is helping our scientists and engineers to do their jobs better. The next one is Transformer, and that's very important for JPL. And as I mentioned, we had, Mars helicopter, Mars rover, and they need to work together. What if they were actually one system? So the machine can be a rover and fly. In this one, this is an autonomous system that we put a map of the path that they need to go. We didn't tell that in front of it is a pond. So this machine actually uses the Google map and finds out, oh, I have to go from over this, there's a pond, I cannot just swim. So I fly. So the mode of operation is decided by the system rather than by the operation. So the final goal is to combine these two for the Mars missions. We can watch the turtles here, how they basically see the intruders. This is actually a current project, and the host of autonomous function that we put on that one eventually also allows this one to stand up and do a segue. Instead of using Google Maps, it would stand up and see better what is in front of it and how to solve the problem. The next project that is called moonshots and transporters, and that is also an important project that uses lots of AI and machine learning. The whole idea is that to be able to have single-person transporters that can be called and can put one person in it and just leave the scene. And you can imagine that from earthquake situation to even in the battlefield when their soldiers need to be taken out. So it's basically designed to carry one person only. The problem that we faced was that even though we don't have a pilot, so it's much better than helicopter in terms of reducing the risk. But once you have a person in it, then you have to make sure that doesn't fall from the sky. What are the national challenges that actually better in this kind of situations? For example, if you want to remove somebody from around this building in downtown LA, or even the Millikan Library middle of the campus, we realize that even in calm day, you have 20, 30 miles of wind around this building. And it's not just a regular wind, it's swirling and all kind of pressure field changes that direct danger to the operation of the system like this. So we asked ourselves, so how do we approach this problem? That's where my colleague Anima and also the others, we're putting together programs that to make this one smart enough to be able to fly into the unknown without going through too much of training. A situation like this, there's no time for training. And every situation like this is different. And you cannot train for all the situations and reduce the risk to zero. So therefore, you have to really rely on autonomous systems that like this one is using the actually AI and machine learning dynamically in order to prevent it from disaster. Now, for example, one idea is that just fly into areas that we call the smart cities. So we have sensors that communicate with the drone or any ambulance that you have and allows you to actually find the safest path in order to go to, say, turbulence behind buildings like this. But situation can be much more complicated. Usually there's not just one building. It can be a complex of buildings that require a different kind of approach. At the center, we have designed a wind tunnel. And this wind tunnel is, we call it turbulence by demand. So I can, for example, put, I want a gust at this frequency with this intensity. Or I want to have a vortex, that hits you. So this tunnel has about 2,500 small fans, each one is adjustable. And we're using actually machine learning to make sure that flow that we prescribed to be produced is produced with high fidelity. Here an example. Here's the tunnel, and this is actually a drone that coming down, but there's a wind going at about 30 miles per hour. And these are little fans, and you will see in a second what happens. So imagine that that now we can create shear or different kind of turbulence, and this is actually a matrix of all the fans, and you can design any flow that you would like to expose machines like this to. And this machine right now using a neural controller that allows it to use its wing and control the whole RPM and the pitch of the voice in order to make it stable. Well, let's go back. The next challenge was that, can we do the same thing for the Mars helicopter? Because on Mars, have high winds. The problem is the density is only 2% of Earth and the density. So it's a completely different aerodynamics. It's a completely different kind of learning that you need to teach this machine in order to handle different situations. So for JPL, the environmental tank, we designed the same kind of fan wall wind tunnel that can produce exactly the kind of wind that Mars, the helicopter will see when it flies around Mars. And we use that very effectively in order to make this a complete autonomous system, and it showed that it really helps by little training on the environmental chamber, considering the Mars atmosphere, how it can be smart and how it can solve the problem. It's still smart. That's the most amazing part of it. The last one, I think, I would say the most important one for us is the partners. Now, we all think walking is granted. You can walk from concrete into grass, and you know what to do, right? You don't fall. But believe it or not, it's one of the most challenging, the functions that you can put in front of a robot. They never show you when the robots fall. Most of them show when they flip, and but the others sometimes they fall and they crash. So our group at CAS, really the Aaron Anderson and Joel Birdie, they're using machine learning and AI in order to teach these robots, not only teaching, let them learn how to handle situations like this. Because it's infinite variations of the same thing, go from grass to concrete to that. Now, of course, this is good for robots to build. But what is it that's really important from we gain from this learning is when we try to design, the system that assists people that they need to actually use this system without falling or hurting themselves. So again, it really goes to philosophy called saying how we bring machine and human together in order to help them, either to do their science or engineering better, or to help people that has an important societal impact. And this machine, aside from being really a mechanical wonder, totally depends on the type of machine learning and AI that the software actually allows this thing to be safe and usable. Towards the end, I'd like to say that, we, for every of these challenges, we are bringing different aspects of machine learning than the AI, like for explorers and transporters, that basically like the distinctive fine-grained, active control, which is the main challenge of machines like that. And deliberative, regarding that, mission is defined, go ahead to multi-agents transformers, especially for the missions like Mars missions. And the last one, the behavioral, which we like to have machines that they're always aware of the human body. For example, think of prosthetics or even insulin pumps. That imagine that every second knows what is the level of insulin or blood sugar, and actually adapts itself based on training it has seen using machine learning in order to make sure you have the most optimal results for the patients or for the person that's using it. What is needed? I mean, for this is my selfish things, for aeronautics and flying and better airplanes, is that we need to have really a dynamic learning. And when we face situations that we don't have any opportunity to do training. So we are really thinking about how to reduce the mission of this, but increase the mission of what information is available. Can we just do things that we already someone else somewhere else has done? and that information is available. Like, in this case, it's the program that started at JPL called Audrey. It uses extensively information is available on the internet. And the results are amazing and reduce the amount of time that you spend to train these machines. One example was that they looked at, they showed to Audrey a video of a rocket, that was launched by somewhere in Korea, and it exploded. And this machine, no training, didn't know anything. It went actually found the literature in Korean and Chinese and Russian, and finally found out that one of the gaskets in one of the rocket engines actually failed, and very correctly predicted that. Okay. So of course that one we knew the answer, we could check, but what happens for cases that we don't? So if you ask me today, what we need is that machine learning and AI approaches that reduces the training. So we can actually use it for situations that we have almost no ideas what we're going into. Okay. With that, I stop and thank you for your patience.
Right, question.
Of course, I leave all the top questions of machine learning to anyone.
Can I ask a little bit more about this last point? So for encountering situations that you don't know about, one could generate synthetic scenarios in simulation. Is that something that your group does? Basically, artificial versions of these embodied objects and using that as a way to explore?
Yeah, that's especially the flying part. And we have two objectives. One is that you will do a different
Can you hear me now? I'm sorry. So we have two objectives. One is that to be able to predict using the sparse data on say airports and see what kind of gas coming towards us. That requires that we predict things within the 10 milliseconds at the normal speeds. That's a big challenge. The next one is that, as I mentioned, that what happens if you can use information that is available to you, not just on board, right? So, for example, we are using 5G on top of this drones and flying this into the winter. But 5G also assumes that you have other informations from, say, sensors on the ground, weather prediction, weather satellites, and everything else. We're trying to see if we can use it in order to avoid, that catastrophic situation. So that's our.
But do you have scenarios where just in silico you have a flying object that encounters those diversity of situations that you can, instead of having to do it with a real embodied object, the virtual embodied object, is that something that one can do? Is it possible to create synthetic simulations that are accurate enough that you could use that for training?
One scenario that we are working on is the weather pattern that created by fire. Okay. When there's a fire, say in Southern California, it creates its own weather, which there's no way to predict because it's spontaneous. Okay. Now you'll enter a situation like this. Definitely, you need to have some sort of predictive tools. And why is that important? Because it causes instantaneous fire. When the temperature rises, also it explodes. Those are examples that we're trying to simulate. And we're working with some firefighting system that groups that helping us whenever something like that. We bring our machine, we take videos and try to see how much of it we can create as a training, pre-training.
Yes, may I ask a question? It's fascinating to see your helicopter flying in the turbulent flow. I'm wondering if you try to do swarm robotics under similar conditions. I'm imagining a flotilla of such drones that are interacting with this turbulent flow and at the same time try to move coherently as a swarm.
Well, that's a different level of. I tell you examples that we tried. We tried 3 drones. Each one carried 1 camera. They tried to make a stereoscopic image of a scene. For geologists, it's very important because you see a rock over there and they want to get an image, right? So coordination of this tree and the turbulence is a problem we have not solved yet. Because for the resolution that you want to sub-pixel accuracy, we are not there yet.
Is it possible that when you make n large, things could become easier because you have like a fluid of active gas moving coherently inside the turbulent one in which they're embedded?
Yes, but I have to think about that before.
Hi, Maureen, I actually have a question. I loved that toolkit that you had up on, maybe it was just the previous slide. But I didn't see, maybe I missed it, but I didn't see anywhere obvious in that a decision-making point. And in the sort of autonomous type systems that I've been thinking about for controlling, physics facilities, that's one of the major pushbacks that I get from colleagues, which is, oh, but at some point you're going to make a decision to change something. And how do you simulate that? How do you make sure that that decision isn't going to cause us to lose our very valuable data? Of course, you talked about losing actual lives. So how do you implement that decision-making process, which is like, okay, some threshold on some quantity or set of quantities has been reached, but the system may need to itself change that threshold based on some other criteria. That seems like a very human, complex, we do terribly at making good decisions sometimes. Can you comment on that?
Audrey is not yet a dynamic system in terms of making decisions. It's mainly designed to assist, for example, firefighters. Okay? So at the end of the day, it's a firefighter that decides a threshold. The action is by the machine, but thresholds. But then we have another situation where we actually you have a drone pilot, and this drone pilot actually flew this drone into that wind tunnel. And we recorded the way he actually reacted. And then we used that as a kind of, I would say, guideline for the machine to make decisions. Okay. Still, of course, from one pilot to another pilot is different, but we trust that the ones that crash, the minimum number of the drones are the good ones. So we have two of those, and we're working to how to map the brain into this machine directly. It's a tough problem.
I have a question. Thank you. It's very good talk. Actually, I especially like the idea of dynamic learning to deal with uncertainty on unexpected, like unpredictable situation. But I have one question. Just wondering if you have ever done the research on the boundary of this capability to deal with uncertainty or unpredictability. Because in real world, I don't think you can design a machine to deal with whatever uncertainty you're going to expose from the environment. So I think if there's a study of that limit, they say, if something happened like that, I need to withdraw. I need to basically do some safety protection, just like this is another layer of thinking on decision making.
Of course, the machines that we have experience with what is the dangerous parameters that this machine should not enter. Okay. So these are kind of predefined in terms of safety is the most important thing. Right? And again, the group within class working as a safe line, like they basically define the parameter space for high-speed racing that we're doing. And those are kind of things we have better control in terms of under no circumstances go into that zone. Okay. But for the machine to decide, it's going to be difficult because the machine didn't pay for it. Okay. I paid for it. So I decide whether I can sacrifice it or not. You use drones, for example, create drones that we fly into the big one you saw. We have also those chip drones that they're about $30. And we use them as a probe. So the drone is big one, mothership is here. We send these tiny drones into the flow, and we just watch it in the sacrifices in order to save the other ones. So these are kind of strategies that we have to think, but at the end, it's kind of policy, issue. And those policy issues, I think, at the end, it's going to be more political than economical and political than anything.
I see, so basically, that boundary has to be, what they call the, trial and error tested in the real time. Because like, for example, for that wind around the building, like there's a limit, if the wind is too strong, no matter what drone you put there, they're going to kind of blow them out, right? So your idea is try to test those boundaries, like, and
Remember,
real
this
time.
this machines, for example, that I use, they know what kind of accelerations and what kind of winds they're gonna be hit by, right? And we set the threshold for that. We don't want the, for example, the blades on the roads to break. So we have a limit. Or we don't want the structure by itself go through vibrations that, throws the GPS on, right? Or the other sensors. So those limits basically is like I know on my ear, I shouldn't expose it to explosion, correct? So those are kind of already defined for the machine. But beyond that, it's a policy, like, don't hit person or don't cross this minefield, or those are kind of different studies.
Thank you.
Thank you. Questions? We can invite more again.